Hello everyone, my name is Frederico Direito, and the theme of this presentation will be crack tip monitoring by multiscale optical techniques, the techniques being digital image correlation, or DIC, and electronic speckle pattern interferometry, or ESPI. This presentation will be divided into several topics, starting with the introduction stating the motivation and objective set for this work. Followingly, the system setups will be shown, exploring in detail each of the system's components, and while also showing the assembly of both setups and the specimens that were used in this work. The system's operations will then be explained, exploring the methodologies for both DIC and the SPI system, with a small detail of the mask drawing process for the SPI, which will then be explained. The results showcase, exposing the crack length and strength-centricity factor values obtained from both methods, with a comparison between methods and also to reference values. Finally, at the end of the presentation, the conclusions that were drawn from this work will be presented. Fracture mechanics is a subject that is increasingly being explored due to its importance in engineering. It's possible to predict the behavior of structural components even when they present flaws such as cracks or fissures, enabling predictions about their maintenance needs. The motivation for this work falls precisely in the fracture mechanics' increasing interest. Most methods that allow the structural health analysis are in situ. With the rise of non-destructive evaluation methods, the applicability of optical methods was considered. DIC is an already established method, but the SPI is rarely used for this type of applications. INEGI's 3D SPI setup was an appropriate system to study the capabilities of this type of methodology. As such, the objectives of this work are studying the applicability of the SPI system for fracture analysis and then compare it to DIC technique and other reference values. Demonstrating now the system setups, it can be discussed that the main components for both of the methods are the light source and the camera. In the case of DIC, the light source is an halogen lamp with a power of 250 watt, and the camera is a 4 megapixel point-grey gazelle with a modular focus set attached to it that includes a C-mount camera adapter, M52 0.75 lens adapter, an extension tube and a 60mm Rodagon lens. It is also worthy of note that the specimen must possess a special speckle pattern on its surface for the DIC process, which was painted on using a welding defect revealer. The SPI system possesses more components, but at its basis the main ones are still the light source and the camera. Due to its high resolution, the positioning of each component must be extremely precise. The light sources, in this case, are embodied by two laser beams vertically aligned, which will be called Y1 and Y2. Even though this SPI setup is prepared for 3D measurements, so 5 laser beams are available, only 2 were used because only in-plane vertical deformations were being studied. The angle of incidence on the specimen is extremely important for the displacement calculation. The used camera is a 2 megapixel Basler Ace with a Linus MAVC 25mm lens attached. As the SPI system used the phase shifting interferometry technique, it is necessary to induce a phase shift in one of the laser beams. For this purpose, the Y2 laser beam is positioned on a linear piezoelectric actuator and the Torlabs piezo controller is used for the movement. Showcasing now both of the systems assembly, they were both aimed at the tensile machine used for the experimental work, which was prepared to hold middle tension specimens that will be observed further. The assembly was done in such a manner that it was possible to utilize both systems at the same time, but the different lighting necessities ruled this option out. As the interferometric techniques that the SPI system uses are extremely sensitive to vibrations, the experimental work was carried out with both systems on an optical table. Briefly introducing the specimens that were used, they were middle tension specimens made of an aluminium alloy AA6082T6 and manufactured according to the ASTM E647 norm. The dimensions are presented on the image and the table summarizes their material properties. All specimens had a thickness of 3 mm. Beginning now the study of the system's operations, the first analyzed system is DIC. The DIC operations are quite simple. At its core, only a picture of the reference state and the formed state is necessary. For the experimental purposes, several pictures were captured at intermediary loads. All the processing was done utilizing a software, VIC 2D 2009, which calculated both displacement and deformation fields. Post-processing was also enabled by this software that allowed the exportation of the obtained data. The SPI system methodology is more complex and requires several steps of mathematical manipulation. First, both the reference and the form states are captured in sets of 4 images each. Then, utilizing all the captured images, the phase map is calculated using the Carriers methodology. Once the phase map is obtained, it's necessary to proceed to the filtering process. A windowed Fourier transform with an algorithm developed by Kamau is utilized. The unwrapping process is the next step and is executed by using a quality-guided unwrapping algorithm also developed by Kamau. As the unwrapped map is in radians, a conversion from angular scale units to length units is necessary and easily carried out using the shown equation, with phi being the unwrapped phase map, lambda being the laser's wavelength, and alpha being the angle of laser's incidence in degrees. Finally, it is also possible obtaining the deformation field by differentiating the displacement field, obtaining this way the strain values. As a small detail, in the unwrapping process, it is necessary to hide the empty areas as the process is extremely sensitive to discontinuities. In order to hide the empty areas, a mask is drawn, but with special care so sensitive data isn't deleted. To restrict the hidden area to the minimum possible without affecting part deformation, a manipulation of the unwrapping process was developed so the deleted area was adjusted to the crack length. This methodology also allowed the measurement of the crack length that is needed for the stress intensity factor calculations. Showcasing now the obtained results for both methods, the first is the crack length measurement. For DSPI, the just presented methodology was utilized, but for DIC, manipulation of the obtained data in MATLAB was necessary. Then, the obtained values were compared with the crack length obtained from the traveling microscope method, executed right after the fatigue loading for the crack generation. The results are all extremely close, with the highest difference being between ESPI and traveling microscope method. The error between DIC and DSPI is extremely small, and the disparity between both DIC and ESPI values with the traveling microscope value may be explained by the repeated loading of the specimen, which might have expanded the crack. For the stress intensity factor calculation, strain values were utilized, obtained from the deformation fields. An area of 4x4 mm after the crack tip was selected and, using an over-deterministic algorithm combined with the Williams series expansion, the mode 1 stress intensity factor was calculated. The utilized equation is visible in the slide, with r and theta being the polar coordinates of the points with the crack tip as the reference point. An example of the deformation fields for both methods is here presented, the ESPI system and the DIC system respectively. Both the appearance and the values of both deformation fields are extremely close, and that fact allied to the crack length measurement for both methods being extremely close, as the stress intensity factor calculation relies on both, it can already be expected the values obtained from the stress intensity factor calculation to be also extremely close between methods. As already expected, the calculated stress intensity factor values between both systems are extremely close, with an error percentage of 1.45. The reference value is the value calculated from the ASTM E657 standard, presenting also very small margins of error when compared to both experimental systems. The comparison between DIC and ASTM standard resulted in an error of 1.17%, and the comparison between ASPI value and ASTM standard value resulted in a margin of error of 2.60%. Concluding the presentation, it can be stated that, concerning crack length measurement, both methods have been validated, as the values obtained in both methods are extremely close one to another, and also extremely close to the reference with a margin of error of below 5%. As it's been referred, the relatively high error percentage might be due to the expansion of the crack that happened in the time between the traveling microscope tests and the experimental work due to repeating loadings of the specimen. In regards to stress intensity factors, with the crack length values so close to each other, the only factor that could affect the calculations were the strain values obtained from the deformation fields. As the deformation fields obtained in both systems are quite similar to each other, both in appearance and values, the only possible result was the stress intensity factors calculated also being very close to each other, which is verified. When compared to the reference, calculated from the international standard, the error percentages are also very low. Thus, it can be concluded that both methods are in unison as both analyses, even though the methodologies are quite different, ended up obtaining the same results, which were validated by the reference results. As such, It is viable utilizing any of the two presented techniques, or even both at the same time as a form of redundant analysis. That is all, thank you for the attention.